はい。Okay. Shall we start? Okay, last time, so we talk about what we talk about a bit of the primary field and also the correlation function. Of the primary field. Prime operator in general dimension. Or whatever. So that's what we, and also we talk about, before that we talk about radial quantization. So the correlation function, whatever, so you consider the path integral Oh, it depends on if it is Euclidean, we should do that like this way, weak rotation. Euclidean, Minkowski, whichever is okay. We consider this kind of correlation function, and then we consider so conformal invariance. We consider it should be conformal invariant. Tell you that the O, so the last time O2x2 is equal to something like this one. Something like this one. In addition to that, what kind of condition do you need? Okay, delta 1 will be equal to delta 2. That's what we did. And O1 x1, O2 x2, O3 x3. And then 1, 2, 3, and then x1, 2, delta 1 plus delta 2 plus delta 3, x2, 3, delta 2 plus delta 3 plus delta 1, and x3, 1, delta 3 plus delta 1 plus delta 2. That's what we saw last time. So that's a conformal invariance will require, and actually I didn't rigorously derive this one, so special conformal part is still like I didn't provide a rigorous derivation, so that's the homework problem, one of the homework problems. So you guys already know, right? Received this homework problem in E-learning. Good. Fine, that's the case. Yeah, I think, and then 4-point function, is much more complicated. And we will deal with this later. We will deal with it later. So this is a later. Hopefully, we will definitely come back on this one 2D case, but the high dimensional case, I'm not sure if we can reach there. It depends on time, how the speed of this course. Anyway, so the speed, I'm not gonna go so fast this course. Hopefully, so far, the level of my lecture and the speed of my lecture is suitable for you guys. I mean, just if it is too fast, just let me know. If it's too slow, just let me know.
adjust a little bit. Anyway, so there are two courses at the semester about conformal field theory. Seems like they are a bit more advanced and seems like a bit more bit faster. So if you want to know an advanced topic, you should go there. So this course is a bit more elementary. So that's the purpose of this course. Okay, so that's 4-point function. So there is some ambiguity. So this is a function. There's ambiguity come from ambiguity. I mean, if you only use invariance, we have ambiguity where this u and d is called cross ratio. So the function written in cross ratio is really the ambiguity, which needs to be fixed by whatever. Bootstrap and so on. Last time I told you like this, right? Sum of alpha, whatever. 1, 2, 3, 4 is beta. I hope that's what I wrote last time. Like, and then at this junction, you need to apply OB. You need to apply OB. You need to apply. Okay, that's what we need to do. This one I will come back later. So now, so we will focus on two-dimensional case, 2D CFT. So from now on, so a couple of lectures, I think like at least coming 5 lectures, I will only focus on two-dimensional conformal field, and I will determine 4-point function later, 4-point function in two-dimensional conformal field. At least 5 lectures is only focus on 2D CFT, and then develop the intuition. Okay, so that's what I told you last time. Okay. So let's do the very, very basic thing from now, and then so as I mentioned last time, d equal to 2 and d equal to greater than 2 is a clear difference because I mean here conformal transformation is something like a homomorphic function. This is an homomorphic function. And then this can be written, if you do the orthogonal expansion, it can be written like e to the mana, e to the order. How did I write it down? Here I have a printed copy. So this is something like infinitesimal transformation T plus like this way. Like this way. Our function like this way. That's the and if we consider this E as the infinitesimal version. And then the infinitesimal version of the transformation is generated by like this way, like this way. And then if we consider, we consider the bit algebra. Anyways, like this. So that's, and d plus 2 cases, they're not infinite, but in general. I mean, just recap. P, K, recap, J, U, and what was it? D, and like that. And here, the corresponding algebra is L1, L0, L1. Okay, so that's what we saw. Okay. And then, yeah, so this is globally defined. in the Riemann sphere, but whereas I shouldn't use the capital at this moment. Okay, and then one of the goals today is to do the central extension. So this is called central extension. So one of the goals today is to do the central extension. Okay, so that's and if you do the central extension, then you will get the so-called Bjorn's round. That's one of the goals. Fine. So that's the goal, one of the goals. Okay, before doing that, so we'll do some recap of this transformation rule for field and so on. I mean, we just do a bit more reverse. So, for instance, you have the recap of whatever symmetry transformation, and then Ward-Takahashi identity. So that's the so if this field is transformed under this transformation, so there's a transformation with the space-time, field is transformed like this way, and then we just consider on a vector. So we consider. So, for instance, if it is the rotation, x prime is something like x prime mu, is something like a lambda mu mu, or rotation or Lorentz transformation, whatever it's called, phi prime lambda of x, and the u of lambda phi of x. So that's a transformation rule we will get. But for instance, this one is something like e to the I omega rho mu s rho mu, whatever, maybe 1/2 phi of x, like this one, it becomes like this one. So this is a global transformation. If you make it infinitesimal, this will become like if infinitesimal, this will become 1 minus 1/2 I omega rho mu s rho mu minus I. Okay, so that's the rotation like this. So as I mentioned, if the phi is a vector field, like phi is any. So if phi is like a mu of x, the rotation will become something like lambda mu, a mu of x, right this way. That's the transformation rule we consider. And if it is Dirac field, I don't remember the detail. Unfortunately. So, in the case of Dirac case, the Dirac field or fermionic case, often this way is proportional to commutator of gamma matrix. Commutator gamma matrix. And for scalar, it's just trivial. It's just trivial. Okay, so trivial. So that's the translation rule. So it depends on the field. U is trivial. This U lambda is trivial for scalar field, for vector is spin 1/2 and so on. Depends on the field, it will get different way of transformation. This is the rotation or Lorentz transformation, rotation or Lorentz transformation, and then scaling transformation. Scaling transformation is like x prime is mapped to lambda x. So then field is transformed. Lambda x is transformed lambda to minus delta of phi. So this, and we call this one scaling dimension. Scaling dimension. Okay. So let's okay, so for instance, if you consider this is free scalar example, free scalar is something like Lagrangian is proportional to phi mu. Okay, proportional. I'm always careless about the sign and the coefficient, so be careful. I mean, Chinese students are very good at like pointing out details. So, I mean, if I make a mistake, please let me know. I'm very 粗心大意，所以 it's better to be careful. So this is the case. So what I'm doing. So here the scaling dimension is 1. So scaling dimension is 1, and the scaling dimension total should be the d. So therefore, d minus 2 over 2 is the scaling dimension. This usually, classically, in the free field. So that's the case. So that's the scaling dimension you will get. So for free field. For free field. But if you have some interaction term and so on, I mean, also this scaling dimension, classical scaling dimension will change quantum mechanically. So that is called anomalous dimension. So this if you add this interaction term or like a potential, whatever you call it, this will receive also quantum friction. So that's called anomalous dimension. So yeah. So that's a scalar dimension. So therefore, one can just consider infinitesimal transformation. I mean, so those are some, these are global transformation we consider. So this is a global transformation. One can consider infinitesimal transformation, x prime. Something like x mu plus omega a del x mu del omega a. So phi prime x prime phi x plus f del, like this one. So the Kali f is written over there. It's just this one. So Kali f can be like the u of lambda, or like u of lambda and lambda to minus delta. So these are like in total. It's just symbolically just call it Kali f. So these all the field transformation I call it. Then, of course, delta. So this omega is infinitesimal. This omega
is an infinitesimal translation generator. And delta omega phi of x is equal to phi x minus phi x, and this is given by delta x mean delta omega a partial mu phi, and then minus delta f. Okay, fine. So that's the case. And so that's the case. Times omega a, and maybe some signs missing. Let's see. Most likely, I need a minus sign here. Minus. So that's the. So since here is x, so you need to bring this one to here, and plug that into here, and then do the tell x, just keeping the leading order omega a. So that's what you get. This one. And this one I call it. The generator of the transformation IG, capital G. That's I call it IG. Okay, let's look at the example of this one. So in the case of translation, okay, I think. Okay. So in the case of translation, so f is always trivial. Capital Kali f is trivial. So I mean, phi of x translation is always phi of x plus a, like this. So it's just nothing will occur. Nothing will occur. Translation is just. So therefore, this is the trivial case. So IGA is something like a mu is minus I, like this one. Okay. So that's the p nu, and then in the case of the dilaton, so that we already knew, minus I x nu partial mu minus I delta. Okay, let's look at the. So here, so we treat it as like a lambda. Okay. So let's get this one. So x prime is lambda x. Sorry, lambda x. Okay, maybe I should write down like this way. X prime, and I just transform like this way. Okay. So then, if you do the transformation, if you take a derivation with respect to omega, you get the x, right? X mu. So therefore, okay, which is I call it? The first term, you get the x mu del mu. Okay, from here, if you take a derivative of omega, you get the x mu here. So x mu del mu, up to some sign anyway. So, and then as I promised, I'm very careless on sign, so you have to fill out detail, that's all. And delta is really coming from f. F is something like this one. And then f is the is something like 1 plus omega, like this way, minus delta. And if you do the tail expansion and so on, you just get minus delta omega. And you just take the derivative of omega, you get this one. And up to psi, you have to be careful about psi. And I'm not going to do the detail, as I promised.
Yeah, I think if I do some detailed calculation, I'm pretty sure I will make a mistake. So up to sign is okay. Okay, so then translation. So this is dilatation, and then rotation. Some of my engineering role here is something like as I mentioned. This one, I mean, you can feel the detail by yourself. So this is the rotation generator and the class S rho. That's the rotation generator. So S is written here. It's written. So why? So that's I already explained to you guys. Okay, and then let's consider the classical theorem. So classical theorem is I forgot. 1904? I don't remember. I think that's further remember. I don't remember. Question mark? Oh. Okay, so then, so this means states that given the continuous, if there is a continuous symmetry, then there exists a constant current. That's the statement. Okay. So, and then later, so mid 20th century, I mean, people just bring this one. This is classical field theory. Theorem classical field theory, very important one. Ward-Takahashi word, and then Takahashi. I think in Chinese like this one. I think. Takahashi, who is that? Schwinger Dyson. Schwinger Dyson just brings the theorem in quantum version. Now it's called Ward-Takahashi and NT. So that's we are going to talk about. But if you want to a bit more, I mean, some of you maybe are heard of it. So this is mid 20th century, like 1950 something. 1950 something. So that's the I'm going to talk about. But this course I'm not going to talk about. And then 2014 is so I mean, in my opinion, there is like a 3 steps to understand symmetry in the field theory. So this is a classical one, classical field theory is a theorem more than a century ago, and this is the quantum version of this symmetry. In 2014, there's a breakthrough of symmetry. So boosting and then cyber they just call now it's called high form symmetry and so on. I mean here so this one I'm going to talk about. This one clearly uses the path integral formulation of this quantum field theory. But this one you don't need the path integral and so on. Symmetry is much more become much more sophisticated and much more broader in this breakthrough. It's called higher form symmetry. I'm not going to talk about it. It's a breakthrough, but it's higher form symmetry. So this is usually when you are a student, you only learn these two up to the graduate courses. But I just remind you there's some other breakthrough in the history of the understanding of symmetry in human being made a significant step into the work. But I'm not going to need it. So from now, I will just introduce these two. Okay, let's derive. Okay, so let's consider this one. This one is symmetry. Let's consider. Suppose this one is symmetry. This one is symmetry. Suppose this one is symmetry. Suppose. This guy is the symmetry of the action S. Then this transformation action is given by dx. New action of the transformation can be written like this way, and then do the infinitesimal transformation. Okay. So then, if you do the transformation rule, you should just consider this transformation. It's just do the infinitesimal transformation. What we get as follows: dx prime, and then you have the measure is something like this one. So this is Jacobian. So this is the Jacobian, and L is the something like the f of lambda, f of phi of x, and then this is the f of start transformation. Okay. Then we plug this infinitesimal version into here. Okay. Then at the end of the day, what you get is as follows. Transformation rule. I'm not going to write down everything. At the end of the day, you get this one, dx, and the ja mu, and the partial mu on omega a. Where this guy can be written. I'm not going to derive everything. It's straightforward calculation. It's really straightforward, which I already written in the note. So there's a middle step which I don't want to write down because it's straightforward. I just plug this one, plug that one into here, and they just expand it. And the first order omega. So that's it. I don't want to do that, to be honest. It's super easy calculation. Okay. Then you get this one. That's what you get. Yeah. That's what you get. You just take a leading order. And since we know the plus S, plus S, plus S. Okay. Plus S. I want to do written here. So the difference between S prime and S are just this term, just this. Okay. So I mean, this calculation I highly recommend to do it by yourself. I mean, it's super straightforward, but I'm not going to do it. So now, if it's symmetry, if it is a symmetry, means that this one should be up to total derivative if omega a is a constant. So then if you do the integral part, this means that if this transformation symmetry, that means J mu is equal to 0. That's what it means. So that's the conserved current you get. Integral part. So let's look at the example. Okay, so then, okay, suppose you just did a Fourier transformation. So example, so x mu is equal to, goes to x mu plus omega mu over x. So this is a Fourier transformation you consider. Then what you get is just coordinate transformation. So here, if you look at J here, you don't need to worry about this one. You don't need to worry about this one because the F is just do nothing for Fourier transformation. So F is trivial, and then you just need to be careful about this one. So what you get is the what you get is the delta S, which is S prime plus S, is equal to ddx and T mu down mu omega mu. So that's what you get. Where T mu is given by minus A mu L plus del L partial del mu phi, and then del mu phi. That's what you get. And often people call it, this is stress energy tensor, stress or energy momentum tensor, or stress energy tensor, whichever you call it, store as energy tensor. Stress energy tensor. Okay. But usually, I mean, it depends. So this is the field theoretical way to derive this. I mean, this is not the correct way of deriving this one. So usually, okay. So I just quoted Schumann. Quotation mark. Usually, stress energy tensor T mu nu should be defined as follows. What's that? Delta S delta G mu nu. And then you have to be normalized appropriate manner. What's the normalization should be? Sorry. Oh my goodness. No. Sorry. What's the normalization should be? square G over 2? Sorry, I don't remember. Some number. Okay, proportional to this one. How to normalize it? Square root G just multiply square root G. Cube square root G. Is it okay? Is it the right way to derive? Okay, good. Okay. Up to some. Depends. So this is the natural definition of stress energy tensor. So this is natural way of doing stress energy tensor. So since the metric is the symmetric, this is symmetric. T mu is symmetric always. This is the case. But this one is not necessarily symmetric. Symmetric? Not necessarily similar. I mean, but often symmetric. Some nice Lagrangian, this is symmetric. But if not symmetric, there's a way to make it symmetrize. But that is just adding like totally antisymmetric. Totally, yeah. Some tensor to add it, but there's a way to make it symmetric. So there's a way to make it symmetric by adding just a total derivative. So that's the so this is the adding total derivative term, to make it symmetric. If it is not symmetric, you can make it symmetric by adding this total derivative term, where this one satisfies this condition. That's how we do that. So this is stress energy tensor. So that of course by consequence of this, so if the action is Coulomb transform, it's invariant Coulomb transformation. Usually this is assumption. I mean, it's just a general covariance of the general activity. So usually this is the concern. So therefore, this T mu, this should be zero. This is the conservation of stress energy. So that's the case. Fine. And suppose and we know the conformal transformation. So let's consider now. Consider the maybe no need to do. Okay. So suppose they consider the CFT. If you consider CFT, what are the consequences of this one? CFT. So suppose conformal transformation is something like this one. Epsilon. Okay. So this is the conformal transformation. Suppose this is the conformal transformation. Okay. So then, the current of this conformal transformation is the current is T mu, is T mu nu, F e nu. So that's the current of the conformal transformation we consider. Okay. So then the conservation of this one is just mean that the down mu plus T mu nu, oh sorry, equal mu plus T mu like this. Okay. So this is the case, and we know this one is 0. This one is 0. This one is 0. So therefore, this means that the conformal transformation will give you mu nu, and we just assume mu nu is symmetric. T mu nu is symmetric. Therefore, become like this one. 1/2, like this way. Okay, and then we use the law of conformal transformation. So this is indeed equal to T mu nu is equal to delta E, and then just appropriate normalization. So that's what we saw. So the conformal transformation we learned is delta mu nu, sorry, mu nu and then eta mu. So conformal transformation we learned before is something like what was that? Is equal to 2 over d delta E eta mu. That's what we learned last before. That's a conformal transformation. So just plug that into here, you get this one. Okay. So this means that the T mu nu T is traceless. This is traceless. So under conformal transformation, in the conformal field theory, so this the stress energy tensor should be traceless. So that's the consequence of this method theorem. Any question at this moment? Okay, so that's the case. Now also we talk about this Ward-Takahashi identity. So Ward-Takahashi identity, so if you consider the quantum version, let's say Ward. So in Chinese this is the Gao-Chao. So you just consider correlation functions of the operator O, and then we just consider the path integral, appropriate normalization path integral of the phi, and then operator O plus delta O e to the minus s. I mean, here is just consider Euclidean version. Dx and then omega A. So like this. So this is the consequence of conformal. So another transformation phi prime goes to phi minus I omega A G A phi. Like this. So another transformation. So this is a symmetry. Suppose this is symmetry. And then correlation function operator O behave like this way. Okay. So this is the transformation under the symmetry operator, and then we know that the action will transform like this. Transform like this here. So that's the case. Then what we get is that the operator O is the dx, and then partial mu. Just do that. You just only look at the leading order of omega. It's something like j mu a of x omega. Sorry. So this is delta. That's what you get. So to be a symmetry of this one, so you just keep tracking all of the omega. Well, first order of omega, and you will get this transformation. So you just do the Taylor's function in omega and bring it to here, and then only look at the first order of the omega, you will get this. Okay, and suppose this the operator O is something like O1. I didn't write down the explicit form of O. But suppose you have like a bunch of the product of the operator, point operator, or n, x n, and suppose O is something like this. So then what you get is that the delta O is something like minus I, sum of I is equal to 1 n, and then O of x1. Yeah, G acts on operator O. G acts on operator O of xi, and A acts on here, and xn, like this. That's how it acts on them. And then I just need to multiply. Then omega A, like this. So that's how symmetry generator axial operator. G axial OI is the derivation of the operator O. Okay, and then let's plug this one back into the here, and then look at the integral form. So to plug this one into here, plug this one into here. Okay, so plug this one into here, and then compare this to this bracket part. Then what you get is a so down x mu, j mu, and then a. Is it okay? So here you have a dependence of xi here, omega. So each symmetry generator acts on each operator, and you have to sum over it. And then when you act as the symmetry generator on the ith operator, the omega depends on xi. Whereas here is independent of the position of the other local operator. Okay? So therefore, to make it omega a xi, you need to include this dot function operator and then take an integral over spacetime. Is it okay? So what I did is something like this one. So literally to get this one into here, literally what you need to do is sometimes you just integrate over dx and omega a x, and also to do the same thing, dx and then times omega. Okay, fine. Is it okay? That's what you need to do. Then you get this one. Fine. Right? There. So so this is called Ward-Takahashi. So therefore, if you plug this network current, so this network current is called network current, and take derivative inside the correlation function. Okay? It's almost zero up to contact time. This is called contact time. So therefore, so there is one. So the intuitive way of understanding this one. So this is x1 or x1 or 2x2 and so on. Or n, xn and so on. And then there's an operator for j of a is also another operator in quantum field theory. Quantum field theory, this is j mu of a x, and then so. But Persian mu, if you act on this one, is if you want the correlation function of this one is 0. So if you want the correlation function of this one and take derivative of with respect to mu of x dx, if they are different, it's 0, but if just this JA approach to the operator OI, that acts as a symmetry generator. Symmetry generator. Okay. Symmetry generator with the data function. That's how you understand. How you understand the Ward-Takahashi. I mean, so I just did all the derivation, so that's also important. The way you need to understand is the Ward-Takahashi is as follows. So if you go to the correlation function with this network current, it's with correlation function, and take derivative, it's almost 0 up to this conductor. So that's the network derivation. Of course, there's some the collision of the operator happens, there's something singular happens. That's what the quantum field theory tells. And that is the dot function with some symmetry action on operator too. So that's the Ward-Takahashi identity. And then that's we already saw number of times. Did I? Okay. Fine. So that's the case. Okay. Okay. So then, what we need to do is that, for instance, so we know that okay, the charges for this symmetry is in fact the d minus 1 x j0 a special circle. That's the how we define. T is constant. X0 is constant. Okay. Okay, so if you have x0 here, and then x1 to d minus 1 here, so this is, you can consider time direction. And if you have a current J here, J0 operator of x, okay, if you consider the J0 operator, sorry, J0 field, no, sorry. So, and then just consider the constant, okay, constant time t, x0 is constant. Special slice. If you consider x0 special slice and then just integrate over zeroth component of the electrical, you get charges. Charges, and then in that case, if you just consider, suppose you have say, so there is some operator O1x1 is sitting here. Only the other operator is the other place, and just integrate it. There is some t minus and then t plus. If you consider t plus, and then you just integrate all this Ward-Takahashi entity. So this is called Ward-Takahashi entity. So integrate out all this Ward-Takahashi entity in this region. If you integrate out this region, then okay. So what I did is the just left hand side. The left hand side of Ward-Takahashi entity integrate out of dx with this region. Is equal to integral out dx this region of right hand side of Ward-Takahashi entity. Okay, that's what we are going to do. Then what you get is that the symmetry generator Q, maybe I mean x0 is constant, or maybe t is okay. So t is equal to t star. T star charges Q acts on T plus acts on. Okay, and no 5 operator on and O2 x2 minus. So it's just the orientation, whatever orientation is. Stokes theorem, by Stokes theorem, if it's one is the orientation is the parallel by Stokes theorem, so the other is the opposite. So that will be the negative side minus operator 1 x1 and O2 x2 and so on. Okay, so that's the left hand side, and it's equal to this one. So delta function just get the 1, right? So delta function coming from here is just here. So this means that the GA acts on operator 1 x1 and operator 2 x2. So that's what you get. Okay. So therefore, the symmetry action on the operator O1 is just commutated on Q and O. So this means that this is what we already see last time. Operator O1. So that's what you do. So the reason why you get this commutator here is that here, your correction function, you always consider time ordering. Okay, time ordering. So t plus is the bit ahead of x1, the position of x1 in terms of time, but t minus is past of x1. So therefore, you have to put this guy have to put the in between O1 and O2. Okay. So now you get the commutation ratio like this. Okay. So charge acts on O1, you get a symmetry generator. So that's the okay. So that's what you have. So that's the Ward-Takahashi identity and so on. And then using this Ward-Takahashi identity from always we consider conformal Ward-Takahashi identity to C. So as I mentioned, so the conformal symmetry, the conformal transformation. So x mu equals to x mu plus e mu of x, and then net current j mu of x associated this one is net current is the t mu epsilon mu of x. So that's net current. And then we apply this Ward-Takahashi into the conformal symmetry and to see what's going to happen. That's the, I think I just do the very, very elementary derivation or like just variation of the field in the path integral or so on to derive Ward-Takahashi in the first half of the lecture. I think it's a good time to stop. And the important part is not the derivation, how you use it. So important part is not derivation of Ward-Takahashi identity, and the question is how we use from now. That's the important part. So the important part comes from second lecture. So let's take a break for 10 minutes. If you have a question, just tell me. Maybe it was too easy for some of you guys, too fast for the beginner, maybe. But just tell me if you have a question. Yes.
I think there's a mistake here.
Oh, okay.
Minus 21 and 2.
Oh, is it the case?
And there's the same in the homework.
The homework too?
Yes.
Oh, okay. Thank you very much. Okay, can you send this mistake in the WeChat? Is it okay?
Okay.
Thank you very much. Thank you very much. Like take a screenshot. And that screenshot is okay. I don't know. I haven't checked your calculation, but I trust you. I trust you. It's a typo, yeah. So there is some mistake in my homework and the lecture notes. So he will send it via WeChat. Okay, can I show you the thing? Okay. So let's apply this conformal Ward-Takahashi to the field. Okay. So let's consider so this is a conformal transformation. So I have to mention the derivation of this one. So what I mentioned in general Fourier transformation, S is something like ddx, T mu, and partial mu epsilon. Epsilon. So under general Fourier transformation, general Fourier transformation. But I mean, usually general Fourier transformation, I mean, it's just any differomorphism. So if the action is invariant any differomorphism, which means that it's much more constrained than conformal invariance, because conformal symmetry, conformal transformation is a subset of a differomorphism. So therefore, I mean, this is not the usually. So if you consider any general conformal Fourier transformation, this is not symmetry of the field usually. So that if you consider that if some mu is translation, then it's just a constant. It's just constant. So then by integral parts you get this the energy momentum motivation. That's the one thing you get. And then if the if it is a conformal symmetry, we can just use this guy as the generator of the natural current. Because I mean, if this depends on x mu, but you can multiply some constant term, this omega. Okay. Then if you consider this one, you can just use this one at the network. That's what I'm going to do. Fine. So therefore, let's consider two-dimensional conformal theory, CFT, and you just consider the alteration of the common operator, and then consider D. Insert x. X. So this is the rationality. So D is some domain. So some domain. So all can be something like a product operator. So O1, O2, O3, and so on. So it can be some product operator, and D is a domain which includes everything. Which includes all the operator, which just includes this one. That's the domain we consider. And then make it homomorphic. So if you write down the Fourier transformation of the z is equal to x0 plus I x1. Let me check. think it's okay. I don't know, it's up to you the convention you consider. If it is Euclidean x1 plus like this one, like this. So we define it this way. So if you define Euclidean, so from now on you just consider Euclidean case, and then define the holomorphic coordinate is anti-holomorphic coordinate like this. Then by coordinate transformation, just a minute. My action is some flow inconsistent. Okay. Okay, so that TCC is like 1/4 of T 2 plus 2I T 1 2 minus T 1 1. This should be, I think. I think this should be okay. Sorry, this is a minus sign. Minus sign, and then T bar is the and then TCT bar is the TRC is quarter of T 2 plus T1 like this. So that's the how we transform. So this if you consider the ZZ coordinate, so you can just use this holomorphic anti-holomorphic coordinate, and then write down stress energy tensor in the holomorphic anti-holomorphic coordinate. Then it's the relation between original and the old coordinate is like this. So therefore, since it's stressless, as I mentioned, conformal field theory is stressless. This is 0. So this. So what we can focus on is this guy, either DZZ or DZZ bar. And then we often, and then we can just write down, this is the T mu, okay, like this. So therefore, we just consider this is T CT del C bar is equal to del C bar T C bar and C bar is equal to C. Is it okay? Do you agree with me? So this is a conservational current. Conservational current. If you take the anti-holomorphic derivative C bar on TCC, then if you take the upper indices, it becomes Z bar. Do you understand what it means? So the metric we consider so metric we consider D squared S is dx1 squared plus dx2 squared. Okay, so this one is equal to dc and dc bar. Yeah, you can just follow from here. Is it okay? So now for metric G is something like G is 0, 0, 1 half, 1 half in the dc bar part. So GCC, GCC bar, GCC bar, GCC. Okay, so like this way. Is it okay? So it's an off diagonal. But if you do the upper indices, So it becomes just inverse matrix. Inverse matrix. Like this. So therefore, strictly speaking, this is equal to, let me think. There is some numbers involved. What should be the case? Maybe 4 here? So to raise the to make it lower z bar into z, you have to use this this component. Okay. You have to use this component. Okay. So therefore 1/2. You have to multiply 1/2 times this component to make it z bar upper to z in lower. You have to make 1/2. Therefore, in total quarter. The derivative of this one is equal to 0. Is equal to 0 because of the because of this net current. Of course, I assume that the del z t z bar is equal to 0 because this is a diagonal component. Okay. Yeah, I assume this one is 0. So therefore, this is the anti-harmonic derivative acts on this guy is 0, which means that the TZT should depend on the holomorphic. Okay? Holomorphic. The same thing happens. TZT bar. If you have the holomorphic derivative, it should be 0. So therefore, it's anti-holomorphic. Okay. So that should be okay. Okay. So therefore, this the you can always factorize into you can always factorize this correlation function into homomorphic and conformal identity homomorphic and anti-homomorphic. So we define the reduction of T of Z is somewhat defined like this way, TZT and T bar of Z bar. Like this way. Like this way. Okay, and then conformal Ward-Takahashi identity goes like this way. Delta E bar for operator O is equal to I over 2 so I over 2. So where did I go? Yeah, this guy. So it's like a D, and then D, C, D, C bar, and then partial D, T, C, D, T, C, C bar, and then epsilon C. Epsilon Z and O and plus V bar D bar C and epsilon Z bar. So that's what you get. This okay. So that's the consequence of this Ward-Takahashi identity. Fine. And then we use this this relation. So this is essentially equal to minus 2 pi times as first remember the CT bar C bar for
simplify TCC form. Do you agree with that? Do you agree with me? Is there some mistake? Did I do that? Hopefully it's okay. Yeah, I think it's okay. Okay. And then use the stock theorem. So and then use the stock theorem for this correlation function. We get the point. So the stock theorem we get that point. No, I mean, I'm not careful about the function. According to this one, this is C minus DC, TC bar, DC bar, operator O, and then plus DC bar, TCC, which is C, and operator O is like this. And then, so we just define this one is homomorphic one, T of T, up to some constant. And this one we just call it epsilon. Epsilon. Up to some constant. And the C is this direction. C is the boundary. So by Stokes theorem, so C is the boundary contour of this domain D. Is it okay? So far, it's straightforward. Then what you get is as follows: minus 1 over 2 pi r C dc equals C T of 2 operator O plus r by 1 over 2 pi r. That's logic. So I use this one. So this term is give you this one after Stokes theorem, and the first term will give you this one after Stokes theorem. Okay. So since it's homomorphic derivative, if you use Stokes theorem, dz will be gone, and dz bar from the first term. The second term, by using Stokes theorem, dz bar is gone and dz. Okay. And then everything here is the first term is homomorphic, the other term is antihomomorphic. Okay, so that's the case. And usually we only look at the homomorphic and antihomomorphic part is very like a storage analysis. So we only look at the homomorphic part usually. Okay. Any questions before? Okay. So that's the case of the Ward-Takahashi. So under conformal transformation, for operator O in the correlation function or operator O, so you just get some contour integral of the just T operator inside, stress energy operator tensor inside. That's what it means. Okay. So conformal transformation is just the sum. It's called. I will explain what it means. Operator product with source energy tensor and operator. So this means that okay. So what we learned is from this
for Ward-Takahashi, so the important lesson we learned is that the conformal transformation in 2D is equivalent to the T of C operator of some function. So that's the equivalent to computing this time. And this is the something of operator product expression. Product. With just energy density. So that's the message. This is Ward-Takahashi stuff. Ward-Takahashi. Okay. So now, so what's the motivation to consider the conformal field theory? Is that the conformal symmetry dictates many. So the apple. I mean, what we need to is consider the conformal transformation of the operator. So we again in the following course we consider conformal transformation of the operator many times, which is equivalent to consider some product with stress energy tensor and operator. That will give you conformal transformation. That's the main message. So therefore, this product with the stress energy tensor and the operator is very important, and this is most important in the conformal field theory in 2D. So that's the main message I wanted to convey. The other thing is that the previous we already did 3 courses at 3 lectures we had. So what we learned is that there's something called the primary operator. Something called primary operator. So O, and then we can define descendants by acting on P mu. Okay, P mu. Okay. P mu and on descendant. And you can act many times. Okay, so this is level 1 descendant, and then level n descendant is all. Okay, and if you act the k also, so this is something like a I don't know what is I don't know what they call it. Anyway. It's lowering operator. I don't know what it called. Lowering operator, raising operator, whichever you call it. I don't know which one is raising a lot. I mean, in terms of conformal dimension delta, this is delta plus 1. So in terms of conformal dimension, it's just a raising operator. But the way we write is usually from operator always the highest, and then just write down descendant in lower. So that's why people usually call this one is called highest weight state. But last time I talk about lower dimensional operator, lowest dimensional states. I don't know last time. I don't know. It depends how you define, how you write. I mean, if you only look at the eigenvalue of D, it's the lowest state. Okay, lowest states, and they construct the representation of the conformal. We will do the same thing. So what we need to do is Okay, so what we need to do is that we're going to do the same thing for this one. And in fact, I don't know, it depends on how you define. So if you act on K, if you have K, it's analysis. And last time at the end of the lecture, I went to told you really completely wrong thing. So the operator O, if you have in 2D, so this is the general dimension in 2D. So you have operator O or states O here, or whatever, states O here. So if L minus 1 acts on O, this is this. So last time, so at the end of the lecture, so if you look at the recording at the end of the last lecture, I put this plus sign here. This is totally wrong. Okay, as I mentioned, I'm very careless, so you have to correct me. So this is lower operator. Maybe L is the, I would say what does, it's just the cross cousin of the beta algebra L, or it's just a central extension of this one. And then you just act on L minus 1 squared, L minus 2, and so on. This is the operator O, and so on. So this is this plays a role. We already know this plays a role P, the translation, and the L1 acts on O is equal to 0 because L1 behaves like a special conformal transformation. Okay, that's we already know. So as I mentioned, small L. And then how you define this operator O? So the operator O, how to define is just L1 analysis this O. Okay, that's one way to define it. Okay. Fine. So now let's look at the conformal weight of this T mu nu, and so on. Okay, to define this primary state, we have to use this conformal transformation or conformal Ward-Takahashi identity, but a bit ad hoc. But let's define a primary operator as follows. Primary operator is as follows: any conformal transformation in 2D CFT primary field. Primary field or primary operator, the phi of t is to behave like this way. So phi prime of w, where w is just w is w of z. It's a homomorphic conformal transformation. Conformal transformation. Find d of that's the transformation. It's very similar to the scaling transformation. If w is just a lambda times c, it just becomes the what we want. So this is in the case of w equals to z, w equals to scaling transformation. So this is a scaling transformation. Okay, transformation. So we have this kind of transformation. But not only scaling transformation, or any conformal transformation, any harmonic function, it behaves like this way, then this operator field is called primary. I will connect this one to this differential later. Let's accept this one at this moment. Let's accept this one definition, and why this is eventually this one. That I need to use this Ward-Takahashi. Okay, let's use this one as a definition. And then this one is just an example. Example of conformal transformation. It's one of the example of conformal transformation, but only one example. The infinite many conformal transformation. This is one of them. Okay. This is one of them. Then again, do that. To connect this conformal Ward-Takahashi identity, I want to see infinitesimal version of this one. Okay, maybe I shouldn't call it this phi. But it depends. I mean, okay. I don't know, operator always okay. I don't know, I mean, it depends on which. Okay, operator O. And this operator O behave like this way. So I only look at the homomorphic part because I'm lazy. So okay. So Z prime is equal to Z minus Z plus epsilon prime. Sorry. Is okay. So this is the transformation rule you get. The first term is really coming from this part. So you just plug this one into here. Plug this one into here, you get this one. The second term is just plug this one into here, and you get this one. I think this should be okay, right? Am I doing some stupid mistake? It should be okay. Let me think. This one. No, I'm just wondering, but this sign's okay. Is it Z prime or Z? Z prime, right? It should be Z prime. Yeah, so this should be Z prime. Okay. So this is the variation of an operator like this way. Okay, and then we know that this one can be obtained from this Ward-Takahashi identity. We know this variation operator can be obtained by this Ward-Takahashi identity. So let's derive that. So then, what should be like here? What should be? How the form look like? Should be look like here. Is that the question? So this is an infinitesimal transformation of the primary operator. We're always a primary operator. Okay, to distinguish, so this is the arbitrary rule. So any operator should obey like this way. So to distinguish the primary operator and the ordinary operator, let's use phi. Let's use that. So phi is a primary operator. Phi is a primary operator. Yeah, I can follow my notation. Phi is a primary operator. So this is the primary operator. Okay. Then how does the T of phi should look like. Okay, so we want the del E of W can be obtained by 1 over 2 pi I. So it's just C dC, and then E of V, 5 C, C minus W. Sorry, this is W. Okay, so that's the square. Sorry, square. So this is to what you learn in the complex analysis. You have a W here, and consider C contour C like this. C like this. So this is a contour C. Okay. And it's a coordinate plane is Z plane, CZ plane. Okay. And suppose this E and phi are some regular in around here. For example, it's a second pole. That will give you the derivative on E, right? At the point W. That's the complex analysis will tell us. It's just a 19th century mathematics. Cosine integers, cosine and Gauss integers. In W, phi, and del phi of W like this. This is also true. So I just only look at this term. So the first term is related to this one. Sorry, I should put the phi here. The first term can be obtained by cosine integral of this guy. Okay. The second term can be obtained by cosine integral of this guy. Okay. And then compare between this cosine integral. So cosine integral here. So then this will tell you that this T of Z phi of W. So I just put the operator over here, phi of W here. Okay. Should behave like what was that? Delta of phi of W C minus W squared plus phi delta W C minus W plus regular term and W. So that's how it should behave, right? So if you plug this one into here, you will get correct conformal transformation rule program. Okay. That's what you get from this one. So the important thing is that at the pole at the W in the at most quadratic here for primary field. And then the coefficient here is a confounded dimension. That's the most important. So this one is the operator product, so it's called OPE with the T stress energy tensor and the primary field phi. Primary field. And then also, so if you do the Ward-Takahashi identity, so Ward-Takahashi identity, so we'll get the Okay. So we don't care about this regular term. So we also do not consider this regular term. We only consider the singular term because we just consider Cantor integral of in the Ward-Takahashi identity like this way. Okay. So therefore, often people just understand this one is equal to thing of the same thing, and ignore this one without this one, without this one, without this one. That's right. We just like use sim and like. Okay, fine. Any question at this moment? Okay, so now, this is how the primary field will obey the rule of the primary field. And so this is the primary field. And often, what we will encounter is that so this is the primary field, but so the descendant, in the case of descendant, people usually get the higher order term, but this one is universal or from the Ward-Takahashi. That's the any question at this moment? Okay, so that's the universal rule. So highest, for this descendant, so the higher order form up here. This is non-zero. That's important. So the difference between primary field and descendant is whether you have a higher form. I mean, whether it truncates at the quadratic form or not. That's the difference. Do you know why? Do you understand why? Okay, let me give you a rough explanation. As many of you, if you have a field or operator in quantum physics, you have to do the model expansion. And usually, do the model expansion is better to do it the cylindrical case. So T of so this Z is the as in explanation. So this is a complex plane. And C of Z is a complex plane we consider. And then here this map to the cylinder, to the complex plane of whatever. Like this way. So Z and W are related to so it should be related to E to the I W. Is it correct? So this is I think you use W. Anyway, so W. I think you use W. Is there some coordinate like in ZW? Okay. Sigma. Sigma? Is that okay? Sigma. So this is a coordinate of sigma. So then here you have a sigma. Am I doing correct thing? I hope I'm doing correct thing. So this is 0, and this is the sigma 1, and then sigma 1 plus I sigma 0 is sigma I use. Okay, and then plug this one into here. It should be okay, right? So is it all minus this? Now I just want to have sigma 0 goes minus infinity is the origin here. Origin. Let's call 0. 0. Let's see. So therefore, if you plug this one into here, you have the minus of the infinity. So that's what we start. E to the minus I sigma. Is it correct? Is it correct way of identifying it? That's why I don't want to do a calculation by scratch on the blackboard. Is it correct transformation? I think some students already knew this is correct sign or not. Or should I use minus sign here and then use plus here? I don't know which one is correct. I don't remember which one should be the consistent given. Anyway, so let me give you philosophy. So let's use the sigma component, and do the model expansion. So I call the model expansion Ln e to the I n sigma, and runs for like this. So this is the model expansion on the cylinder. I use the cylinder component. Usually people just this is a Fourier transformation on the cylinder. Okay, so this is okay to free to do that. But then to move to the conformal transformation T of z, this will become sum of Ln Cn plus 2, where n is and these two really come from this conformal A. Did I erase? I erased. So as I mentioned, so this plus 2 is really coming from the scaling transformation of this t here. So this scaling measure of t is actually equal to 2, and then this shift of 2 is coming from like this way. So more precisely, phi of sigma. Phi of sigma do the same thing. This is more easy to see. Phi n, and then e to the I n sigma. And do the conformal transformation of phi of z coordinate. This will become sum of phi n z to the n plus delta. N is like this. So can you see that? The phi of z should be a d sigma minus of delta phi of sigma. Okay, so that's the primary field. It should behave, right? Is it okay? Should behave. And we know this one is equal to okay. So this one, okay, then I really don't know what to do. So this one is equal to, okay. So what I want to do is something like this way. Yeah, isn't it something strange? Does anyone have an opinion about sign now? Can you see that? Somebody say something.
Just use the also.
Sigma? Like this one? You mean this way? I just want to have this way, the opposite way. sigma. Then I think what I want is this one is equal. So this phi of sigma is something like Ln z to the minus n and z squared. Z delta. That's what I want, to be honest. Up to some quotient. But that's okay, right? It's totally fine. At this moment, it's everything consistent. If I define like this way, z is equal to e to the I minus I sigma, this is okay, right? Totally. It's phi of phi, sorry. Phi of phi. Okay. Is it okay? Do you understand what I mean? Are you guys following with me? I mean, this one is equal to sum of phi n z to the minus n, right? Is it okay? Because I use this definition. And dv over d sigma up to some constant, a irregular constant. I think this one, there is something like a minus I to this sigma. Something like this one will show up. Because of this. But I don't care about this some constant. I don't care some constant. So dv over d sigma is you get the dv over d sigma. You get the z to these. What about z sigma? Do you get this one? Yeah, you get this one. So therefore, the model expansion is something like a sum over phi n z to the minus n minus sigma. Okay, or n plus sigma. Like this. So this is usually the usual rule for doing the model expansion from now, as we will see. So if you do that, just go to the quantum physics course, and then you start learning the quantization of the free scale. That's what you learn first of quantum physics. First things to do is the model expansion or Fourier transformation. Okay, and treat this guy, treat this mode as an operator. Treat mode as an operator. To obtain this commutation ratio mode, is use applied canonical commutation ratio. Okay? That's usually do. We do the same thing in two-dimensional quantum physics. It's just quantum physics. So we do the model expansion, and then for just model expansion on the cylindrical space, and move to the how to say the plane by conformal transformation and do the radial quantization. Radial quantization. Then always you have a shift in model expansion, you shift by conformal dimension, sig delta. Okay? That's a philosophy in conformal physics. And we treat this one as the mode operator in quantum physics. And we will consider this commutation ratio. The same thing we will do. T of z, we will do the model expansion like this way. And I will explain why this conformal dimension is 2 coming due course. It's in fact conformal dimension is 2 in stress energy test. That's easy to see actually. I mean, once you TCC or TGC bar, you have 2 indices, right? Therefore, it's just a conformal dimension 2. That's it. It's very simple. I mean, as I mentioned, so the TMU is just proportional delta G mu. Delta G mu. So this is spin 2 operator. This is spin 2 operator. So it's just conjugate. So therefore spin 2 is always conformal dimension 2. So A is the conformal dimension of this guy, mu. One spin 1 operator is all conformal dimension 1. It's the same thing. Spin 2 always have a conformal dimension 2, so therefore you have a shift by 2 if you do the model expansion. So that's one. Now, let's set the W for simplicity. Let's set the W to be 0. And now I think I can erase this part. So T of z and then phi of z, if you go look at this one, And if you do a mode expansion, this will give you Ln Zn plus 2 and the operator of V. So that's how it acts on. Okay? Is it okay? And then, so now, no, phi. Now I treat phi as a primary field. Okay? Primary field. And then you have a complex spread C and 0, and do a contour interval like this. Okay? If you do it like this, and we know this one should behave like a z-square delta phi of 0 plus maybe I can erase out this part because I know the meaning Stokes theorem and so on. Plus del of phi of 0 of z plus the regular term, which I don't care. Like this. And then compare between these two. When n is equal to 0, n equal to 0, so this one, okay. So this one, if you just write down this one, is just L, say 1 v cubed plus L0 z squared plus L minus 1 z plus L minus 2 z plus total. Right? Like this way. Just mode expansion. And compare between this OPE and how this mode acts on operator phi. Okay? It translates to z squared means that L1 acts on phi equal to 0. Okay? L2 acts on phi equal to 0. So all this higher mode acts on phi to be 0. Okay? It's analysis phi term, analysis phi. So all the higher mode analysis phi. That's what it means. Okay? But L0 acts on phi, you get the conformal dimension. Okay? L minus 1 acts on phi, you get the derivative. Okay? And L2 is much more complicated. Okay? L2 is more. So this is more complicated. So, but what was the philosophy of defining a primary field? What we want is K annihilates operator O equal to phi, let's say. K of phi equal to 0. That's what we want to define our primary field. In two dimension, we know that L1 corresponds to K mu, and L0 corresponds to dilaton or rotation, J mu. And then, what was that dilatation? L minus 1 depends A to P. Okay, that's the translation. L0 acts on phi, we get the conformal dimension. This is exactly the eigenvalue of D. L minus 1 acts on phi, we get the derivative. That's exactly the action of the P. Okay? So therefore, and then L2 here, L1 acts on phi, annihilate. L1 annihilates phi. Okay? You get 0, which means L1 annihilates. But therefore, you get this condition. You will get this condition. So the reason why we define the primary field like this way, primary field like this way is the transformation rule for the under the conformal transformation behave exactly like the K analysis phi. K analysis phi. That's how we define. So therefore, this definition of a primary field is really consistent with this definition. That's what I want to say. Okay, so that's the one thing I want to say. Okay, now we still have time, so let's move on to the simplest example. Any question at this moment? Alright, let's move on. So we can erase Ward-Takahashi and see. Okay. Now, example, let's look at the example OP of the example. Free boson. Free boson is something like a square x function unified. Okay. That's a free boson. And then for simplicity, so somehow I normalize by h5. That's free boson. And then do consider correlational function. So the question is phi. So the scaling dimension of phi is equal to 0 in this case. Because here we have scaling dimension 1, scaling dimension 1. It's already 2, so the alpha phi, the scaling dimension should be 0. Okay. So that's the scaling dimension of phi. And then, but still we can consider like the propagator of this theory. So propagator of this theory is something like a time order of phi of x and phi of y. So this is the propagator of this two-dimensional free bosons. So we can consider propagator, and this is usually the inverse of this Laplacian. I mean, this is what you learn in the so this one usually people just write down like this way, a squared y phi of x minus 4y. So this is the operator x on y and 1. So just people just write down like this. So essentially, propagator is the inverse of triangle. Yeah. Inverse of triangle equation. That's the philosophy. So inverse of triangle equation. So I call this is A of xy. And usually this propagator is A inverse of x. So this is usually what's really happening. So that's what I'm going to explain from now. Yeah. So essentially, what's really happening is that the triangle equation acts on this the 2 phi x. So it's a free scalar, mass free scalar. And if you do the proper normalization for phi, you do the global you get dot function. This is the usual propagator. You can consider this is also definition of the propagator in free scale. So this is true for any dimension. It depends on how you normalize, it's totally fine. It depends on normalization. But if you want to consider propagator or 2-point function of this free scale here, this is delta d x minus y. So that and acts on the triangle equation up to some normalization. So this is the usual thing. So final propagator in scalar theory, when you learn in quantum field theory, you just have A times B is equal to identity. A is the Conformal equation, B is the propagator, and then dot function is the identity. It's very similar. So it's just the inverse. The propagator is a inverse of Conformal equation. Inverse of Laplacian. So that's what it is. So this is exactly what I want to show. Okay. Let me go to philosophy. I mean, not just Gaussian integral. I think so suppose let's accept this one. So if you accept this one, let's see what's going to happen. So this derivation is not so important actually. The important thing is that what are the consequences. So let's accept I will derive this one because I have only 10 minutes. I want to say something important instead of just deriving this one. So let's accept this one. So then we can just use up the fact that so Laplacian of the in 2 dimensions is as follows. So if you consider K, so this propagator is equal to, so let's say this is K of xy, then this should be only depends on K of rho x minus y. It's just that, as I mentioned, the 2-point function is just that if you consider translation invariant and so on, or rotation invariant, it should only depend on the distance between these two. Okay? Then, in fact, the Conformal equation is like this way. So this delta K rho is equal to delta 2 rho like this way, and then you just need to do the appropriate normalization. If you do the appropriate normalization, you get the slope. So here, if you just integrate out by d rho times 2 pi. 2 pi is just theta direction, and then 0 to r. Then what was that? So d rho plus rho. So this is the metric, right? This is the metric, right? For it's correct, right? For plane. This is the metric, right? So therefore times rho, so it has a Jacobian. And Laplacian is really like this way. Delta rho from K prime of rho. This is Laplacian. So this is Laplacian axiom. Is here is equal to. So if you just plug this one into here, you get the. This is the integrated version of this Laplacian, and this is equal to 1/2 times r K times r. So therefore, from here, K of rho, K of rho should be equal to log of rho squared. Hopefully it's okay. So this is equal to am I doing nothing? It seems like there's some issue. Yeah, there's a minus sign here. Sorry. minus. If you solve this Crank-Gordon equation, integral version of Crank-Gordon equation, with delta function, you get this one. So this part is the Laplacian. This part is the Laplacian on two dimension. And then from here, what you get is 2-point function, or sorry, instead of 5. So 5 is for private. I use qualified, ordinary 5 instead of. So the propagator between these two is equal to minus log x minus 1. That's so that's what you get from this analysis in two dimensions. Okay. So now I just did a quick now because I just want to say something important for quick scale, and I will review next time. From here, one can say that the follows. So phi of z, if you only look at the homomorphic part, so this is equal to minus log z minus w. Okay, and if you include the anti-homomorphic part, is the same, and you get another piece minus log z bar minus w bar. At the end of the day, you get this absolute bar squared. So if you multiply them together, you get the absolute bar squared. But I'm not going to include this one. So I will forget about the anti-homomorphic part because it's analogous. Okay, so then from here, what you get, if you take a derivative part of z, derivative part of w, if you do the correlation function of this one is in fact equal to minus z minus w. So you just take the derivative of with respect to z and w here, you get 1 z minus w. So that's what you get from here, from this analysis. So now we do something very naive thing. Suppose you start with this action and compute t mu nu, which is the like this one. If you do this one, what you get is a false. This one is you get like 1/4 pi mu. Like this one minus 1/2 eta mu minus square. So then, if you compute TCZ part, T can be understood as false. Is equal to minus 1/2 normal order product of anyway. Like this. Then now, sorry, I will be a bit, next time I will come back to this point and will explain more detail. I just want to consider this kind of operation. So now we just use the fact that this is equal to minus 1/2 normal. I will explain what the normal order product means next time. But just do naive calculation. If I get something meaningful. Okay. So if you consider this product of this stress energy tensor and this operator, so we now treat this field as an operator at the point W. and consider the product between these two. We know the product between these phi w and phi del phi and del phi. You get 1 over z minus w squared. We do the same thing. The product of this guy will give you delta phi of z. What's left is delta phi, right? So if you take the product of this guy, what's left is delta phi, of which depends on z variable. I mean, it's just simply depends on z. Because you just stress energy tensor only depends on z. And then, if you do the product of del phi, you get the 1 over z minus w squared. And then there are two ways to do the product. Either this way or the other way. Or the other way. There are two ways to do the multiplication. Either this guy or this guy. Okay. Do the multiplication. There are two ways to do the multiplication. So that will cancel one of the three. The minus sign cancel with this minus sign. Okay. And then you get this one. Let's massage this one. Okay, maybe I should write down the equal. Maybe something. This is equal with this, like this way. I want to do a regular part because okay. And to do the Taylor expansion. So let's do the Taylor expansion. So this is at point Z, and if you do the Taylor expansion, it's the second derivative. Or like a first derivative action here is you get the second derivative. Okay. And this is exactly what we saw before. So this is the, if you treat this one as phi, operator phi. Operator O. This is O. And then down O. And there is no higher order pole. Okay? There is no higher order pole. So therefore, this means that the del phi is a primary of conformal dimension is equal to 1. That's what we have from this tutorial. Good. That's what I want to say. The next time I will review how to derive this one. Then I will explain what's the meaning of this operator product. No, sorry, no order product. Just put the annihilation operator to the left. Creation operator to the left, annihilation operator to the right. Okay. So that's the normal order product. And so anyway, so that's how I explain. But anyway, so what I want to do, free scalar theory, del phi is the primary. That's what I want to say. Okay, with conformal dimension. Okay. So let's review that. We go on next time at the beginning. Okay, let's stop.